on you to be in the video. That's a good time to switch it off. And okay, I think you have 30 minutes, but you're the speaker.
Okay, thank you very much. Thank you for the introduction. Thank you for having me giving this seminar about the Imaging X-ray Polarimetry Explorer that, as you just heard, is a new mission that is performing for the first time spatially resolved X-ray polarimetry. In this talk, I will give an overview on why X-ray polarimetry is interesting, how we do it with IXPE, and then I will focus on a couple of its science cases, that is the observation of supernova remnants and the molecular clouds in the galactic center. But let me start by showing you a multi-frequency view of what is probably the best studied source in the sky other than the sun, that is the Crab Nebula. The Crab has been imaged at every wavelength, in radio, infrared, optical, and of course in the X-rays. And in particular, its polarimetric properties are well known from radio to the optical. However, if we look at the X-ray images, we see from Chandra observations that the Crab Nebula exhibits very rich and complex structures with jets, torus, diffuse emission, characteristics that are unseen at other wavelengths. However, when we go to the polarization in this energy band, what do we have? Or better, should I say, what did we have before the launch of IXPE? Just this, a single measurement integrated over the whole supernova remnant that was obtained in the late 70s. And other than this measurement, no other significant measurement was ever obtained. Just a couple of upper limits for other sources, but that's it. And this is a pity, as you can imagine, because while polarimetry is an established technique in other wavelengths, the field was behind in the X-rays. And polarimetry is an invaluable tool for the study of cosmic sources because it adds two other observables that are the polarization degree and the polarization angle to the other observables that we can obtain, to the other information that we get from other techniques such as imaging, spectroscopy, or timing. As you know, polarization is a property of the electromagnetic radiation that arises when there is a preferential direction in a system. So it will be usually related to the to geometrical asymmetries or by the topology of the magnetic field. This means that polarization can be used, for example, by non-thermal emission processes such as synchrotron, by the presence of disks, blobs, jets, but also by radiative transfers in strong gravitational or magnetic field. This means that we expect that basically every high energy celestial source will be somewhat polarized in the X-rays. In this table, you can see that as a function of the energy, we can study with different, let's say, accuracy, many scientific topics, from accelerational phenomena to emission in strong magnetic fields, scattering in spherical geometry, but also a problem of fundamental physics. And I will point out that the classic X-ray energy band between 1 and 10 keV is particularly well suited for study many of them. And this will become important later. So it was immediately recognized after the discovery of celestial X-rays that polarimetry would have had an important role. So why do we have just one significant measurement? Before answering this question, just a brief reminder of the formalism involved in polarimetry in general, and then X-ray in particular. Your typical polarimeter will be made up by the combination of a detector coupled with an analyzer, and in optical, for example, is typically a filter, that allows to detect the distribution of the azimuthal angle, the direction of the incoming photons. So if the incoming radiation is polarized, you will have an angular distribution of the direction of the events that can be fitted by a cosine square function because there is a preferential direction. And then we have a very useful formalism for describing polarization that is given by the Stokes parameters that allows to describe the polarization of radiation in terms of additive flux-like quantities. But when it comes to describe the significance of an X-ray polarimetric measurement, the most important figure of merit is the so-called minimum detectable polarization. that it represents the minimum degree of polarization that you can detect with a certain confidence level. And it depends on the number of accumulated counts and on the detector efficiency. And here, the challenging nature of the X-ray polarimetry manifests itself, because according to the definition of the MDP, in order to claim a detection of a 1% polarization degree with a 99% confidence level, we need 10 to the 5 counts. This is to be compared, for example, with the dozens of counts that can be enough to claim a detection of a source in the X-ray with an image, or the hundreds of counts that are sufficient to fit the slope of a spectrum. So, especially for extended sources, X-ray polarimetry is challenging because you need either very bright sources or long integration time to reach the needed statistics. For these reasons, X-ray polarimetry is said to be a photon-starving science. Going back to the history, so X-ray polarimetric studies started right after the discovery of the celestial X-rays in the 60s, with the first scattering-based polarimeter flying on sounding rockets. But the first result, and the only result, the one of the Crab Nebula that I showed before, arrived in the late 70s with the Bragg diffraction polarimeter on board of the Oslo 8 satellite. But after this result, even if many polarimeters, X-ray polarimeters, were studied and developed for all the major X-ray polarimetric missions that flew after, none was embarked and flew in the end. This is because most of all because of the introduction of X-ray optics, because the previous instrument needed their satellites to spin in order to detect the signal. The introduction of optics made spinning satellites obsolete, and the technology available was no longer profitable and had to compete with other instruments and suffered from high levels of background. So a sort of dark age started for X-ray polarimetry that endured until the first 2000, when finally in Italy, photoelectric effect-based X-ray polarimeters, such as the gas pixel detector, were developed. These photoelectric polarimeters could be put at the focus of X-ray optics, and thence allowed for the development of new X-ray polarimetric missions. How does the GPD work? So the idea is that when an X-ray photon is absorbed in a gas cell, a photoelectron is emitted. And while streaming in this medium, it ionizes it, leaving a track of electron-ion pairs. This photoelectron track is recorded, amplified and recorded. And the important thing is that the direction of the emission of the photoelectron will be preferentially in the direction of the electric field of the incoming photon. So it keeps memory of the polarization state of the incoming radiation. So if the radiation is polarized, we will have this modulation of the distribution of photoelectrons, while if the radiation is unpolarized, the response of the detector will be flat. Another advantage of the GPD is its capability to record the impact position of the photons, allowing thus to perform spatially resolved X-ray polarimetry. And the first mission entirely dedicated to spatially resolved X-ray polarimetry, employing the GPD technology, is the Imaging X-ray Polarimetry Explorer, or IXPE. It is a small NASA mission in collaboration with the Italian Space Agency that was selected for launch in 2017 and successfully launched last December. So it had a very fast development cycle. Italy gave a fundamental contribution to this mission, providing the 3 detector units that are shown here at the base of the spacecraft, that are at the focus of 3 identical X-ray optical modules that are on top of a 4-meter boom that is extended on orbit. So IXPE improves on the polarimetric capabilities of OSO 8 by 2 orders of magnitude in the and adds in the 2 to 8 kV energy band imaging capabilities with an angular resolution better than 30 arcsecond and a 12.8 by 12.8 field of view. It has also moderate spectroscopic capabilities and good timing accuracy. A curious thing is that we developed the IXPE to be launched in this very small fairing of a Pegasus XL airborne launched rocket. But in the end, we ended up launching on a SpaceX Falcon 9 rocket. So the 300 very small IXPE spacecraft was the sole payload of a very room Falcon 9 fairing. So the Falcon 9 placed the spacecraft on a 600-kilometer equatorial orbit, and I had the once-in-a-lifetime opportunity to go to see the launch, as you can see here. So this is instead a picture of the IXPE EAPS team that we took in the occasion of the delivery to the US of the first fully calibrated flight detector unit that we extensively studied and calibrated in our laboratory in the last years. Indeed, an important topic that cannot be overstated when talking about X-ray polarimetry is the fundamental importance of calibrations of the instrument, because the GPD is a new instrument. It has less than 20 years, and it only flew once on a Chinese CubeSat, but without optics and a smaller scope. So all we know about its characteristic and its evolution in time comes from ground testing. And we know that some of its properties, such as gain, quantum efficiency, and internal pressure, change with time. So it was fundamental before the launch to understand the response of the detector to both polarized and unpolarized radiation. And it is again fundamental to monitor the detector properties during the mission lifetime. But there is a problem. We do not have a celestial X-ray polarization source because, as I said earlier, the only source we knew to be polarized in the X-rays was the Crab Nebula, but it is a variable source and it was not known how and if its polarimetric properties changes with time. And the last time it was observed was indeed a non-negligible fraction of its total lifetime, so it cannot be used as a calibration source. And moreover, we cannot even rely on truly unpolarized X-ray sources because we expect basically every one of them to be somewhat polarized in the X-rays. For this reason, in order to calibrate the instrument on the ground, we set up a lab in our clean room facility at IAPS, and we monitored the detector for many years. But then, during the mission lifetime, we can study and calibrate the detector thanks to an onboard filter and calibration set that is installed on a filter and calibration wheel that allows to place in front of the detector from time to time both polarized and unpolarized calibration sources. There are 4 of them: Calais, that is a polarized calibration source, and then Cal B, C, and D that are unpolarized. Particularly interesting is the polarized calibration sources. All of them are powered by radioactive iron-55 nuclides that emit radiation at 5.9 keV. In the case of Calais, part of these 5.9 keV photons are partially absorbed by a thin silver foil and re-emitted by fluorescence at 3 keV. They both diffract to Bragg diffraction on a graphite crystal and hence impinge on the detector polarized. This allows us to study the modulation factor, that is the response of the detector to completely polarized radiation at 2 energies. Then we have the unpolarized calibration sources that are of 2 kinds. There is Cal-D that illuminates a spot on the detector at 5.9 keV in order to study spurious modulation effects. And then there are Cal-C and Cal-D that instead illuminate the whole detector at 2 different energy in order to calibrate the gain. Also, these calibration sources were extensively tested in our laboratories, first with commercial detectors, and then, since there is no commercially available X-ray polarimeter, with the gas pixel detector itself. Now, let's move to the science that we can do with IXPE. The IXPE observation plan is organized so to cover 7 major classes of sources, from supernova remnants to accreting stellar masses black hole, magnetars, accreting white dwarfs and neutron stars, pulsar nebulas, radio quasar GNs and the galactic center, and then blazars and radio galaxies. To each class is dedicated topical working group that is tasked with preparing the observation through simulations and then to analyze the data, because I am legally obliged to say that the IXPE data is public right after the observations. So we as a team must be prepared in advance in order to exploit the data the best. Now, describing the science case for each of these kind of sources would take many conferences. So I will focus on 2 classes of sources I'm particularly interested in, such as supernova remnants and the molecular clouds in the proximity of Sagittarius A star. Let's start from supernova remnants. They are an important classes of extended sources that IXPE will observe. And the first ER target list, in the first ER target list, 3 famous supernova remnants are slated to be observed. From left to right, they are Casei, the Tycho supernova remnant, and SN1006. The X-ray polarization, the X-ray polarimetric observation of these targets will allow us to understand many open questions on the physical processes that are happening in the supernova remnants, such as what is the role of magnetic fields for particle acceleration, and what is the magnetic field orientation at the shock front. So the interesting polarization comes from the fact that supernova remnants are thought to be the source of the majority of the galactic cosmic rays through the mechanism of diffusive shock acceleration, in which the particles diffusively moves towards through the shock, thanks to a high level of turbulence that induces a sort of random walk, and each time they cross the shock, they gain a bit of energy. And the observation of X-ray synchrotron radiation means that at least 10 to 100 TeV electron must be present. They have a very short lifetime, so they are emitted in very small, very confined region with respect to, for example, the radio band. So by studying them, we can probe much closer to the shock that is at other wavelengths. We know that synchrotron radiation is intrinsically very highly polarized, up to 75%, with the polarization angle that informs us on the magnetic field topology, and the polarization degree instead telling us something about the level of turbulence present. Now, from radio polarimetric observation, there is an interesting dichotomy that is observed between old supernova remnants that have mostly tangential magnetic field at their shock, and younger supernova remnants, such as Casei, that instead have an overall radial magnetic field. While the tangential magnetic field can be explained by compression of turbulent magnetic field in the shocks, the radial pattern of magnetic field is still not yet completely understood. There are 2 main schools of thought. One calls for magnetohydrodynamic instabilities stretching the magnetic field across the shock. But it could also be that what we are seeing is but an observational bias due to the fact that even in a random field, the particles are accelerated more favorably in the radial direction. So we are only seeing that patches with radial pattern. From these open questions comes the interest in studying in the X-rays in polarimetry supernova remnants. And actually the first target of the scientific phase of IXPE was indeed the supernova remnant Casei. This is a combined image of the IXPE image of Casei in purple while in blue there are superimpressed the continuum emission from Chandra, from where we expect to find polarization. Indeed, Casei is a very bright supernova remnant that has a spectrum that is dominated by lines, by thermal lines, but there is also a synchrotron continuum between 4 to 6 keV. That is what we are seeing here. It comes from very small regions, 1 to 2 arcsecond width. So from this we can infer 250 microgauss magnetic fields, and a peculiarity of Casei is also the presence of a reverse shock. So materials that of the supernova remnants itself that is shocked. Our goals for this observation were to determine the polarization degree and see what this tells us on the magnetic field turbulence and the direction of the magnetic field. So there are reasons to think that the X-ray polarization degree could be either higher or lower than the radio one that is observed to be about 5%. Because since the X-ray emission, as I said, comes from smaller region than in the radio, they are less affected by depolarization due to the passage through domains with different orientation of the magnetic field. Moreover, the index of the spectral index of the X-ray emission is much steeper than the radio one, and the maximum polarization achievable depends on the steepness of the spectral index. On the other hand, there could be high magnetic field turbulence near the shock that could bring the polarization degree lower than the radio. As far as the orientation of the magnetic field goes, it could be tangential due to shock compression at smaller scales, but there could be also isotropization of the magnetic field downstream, or it could be radial like in the radio, with the difference that now we would probe an order of magnitude lower than in the radio. Being the first target observed by IXPE, this observation, this source represented the trial by fire for all our analysis techniques. And indeed, it was a very challenging observation to study. First of all, it was observed for close to 1 megasecond, but we had to remove part of the data because of a thermally induced motion of the boom of IXPE that was causing a smearing of the observation. This boom motion was removed to an X-ray aspect solution, but there were still a remaining effect that was impacting the image, producing phantom regions that I will show you. So we ended up with about 800 kiloseconds of observation. Then we had to correct the energy scales because of detector-related gain variations. And we did this thanks to the onboard calibration sources. Finally, also, again, because of the X-ray aspect reconstruction, we had to correct the relative and absolute WCS positions. Indeed, this is the practical example of the importance of onboard calibration sources. On the left are the original spectra of the 3 IXPE detector units. As you can see, not only they do not overlap, but the energy scale is just wrong. In particular, the bump where the iron complex emission is completely offset. But thanks to the calibration sources C and D that have a known energy, we could reconstruct the correct spectrum that now perfectly overlaps and allows us to combine the results from the 3 detector units, improving the statistics that we so desperately need for X-ray polarimetric observation. Another thing that I forgot to mention is that we also filtered out likely particle background events, exploiting the different morphology of the background, the instrumental background photoelectron tracks with respect to real source tracks. As you can see, this is not only energy calibrated, but also background subtracted, and we remove the high energy tail and low energy bump. However, we found that this background filtering did not have an effect on the results of the X-ray polarimetric study because Casset is bright enough. This is the effect that I was telling about due to a bad aspect. You can see the plot of the exposition of the events against time, and there are spikes where the source appears to move where it should not. We removed them, we removed this bad time, obtaining a clean light curve. It can also be seen in the images the impact of the removal of both the background and this bad aspect, where some spatial artifacts are removed, allow us to greatly improve the clearness of the image. Now, unfortunately, I cannot show you the X-ray polarimetric result of the Casset observation because I am supposed to present them next week at the AES. However, we expect to publish the draft of the discovery paper on the archive very soon, so I hope you will like the results. Last but not least, I would like to talk about a mystery at the center of our galaxy that IXPE could allow us to solve. Today, we observe Sagittarius A star, and now we also, of which now we have also an image, that is the supermassive black hole at the center of our galaxy, to be relatively X-ray dim, even dimmer than one would expect from a supermassive black hole of its mass. However, in the 300 light years region around it, the so-called central molecular zone, many molecular cloud complexes, such as the one circled in red, are observed to exhibit X-ray reflection features, such as a prominent iron K alpha line and a reflection continuum. The intriguing thing is that there is no source strong enough to explain this X-ray emission present at the time. So the idea is that what we are seeing today is the light travel time delayed echo of a strong activity of Sagittarius A star when it flared to be 1,000,000 times brighter than today, no later than a few centuries ago, and hence more similar to a low luminosity AGN. And indeed, X-ray polarimetry could be the key to answer this mystery. Indeed, there have been, in the last years, there has been many attempts to determine the past light curve of the molecular clouds in the galactic center using X-ray spectral and morphological variability. But the problem is that the distance, the line of sight distance of the clouds is poorly constrained, and this makes difficult to infer the travel times, and hence the number and the duration of the events. But if this reflection is due to an illumination from an external source, then the reflection should be highly polarized by scattering, with the polarization angle being perpendicular to the scattering plane, meaning that the detection of polarization from two or more clouds would allow us to pinpoint, triangulate the position of the external illuminating source. But that's not all, because the degree of polarization will depend on the scattering angle, and hence on the line of sight distance. So with an IXPE detection of the polarization from these molecular clouds, we would not only determine the recent past of our galactic center, but we could also perform a sort of tomography of the matter distribution in the galactic center. This is, however, probably the most challenging of the IXPE observation planned, because these clouds are very faint and are embedded in a thermal unpolarized plasma that permeates all the galactic center. This has the effect of diluting the polarization degree that will be of 100% in the case of a 90-degree scattering angle. Moreover, they are very faint, meaning that the instrumental background will be a non-negligible problem. And there will be also morphological smearing of the source during to the limited point spread function of the instrument. And also the cosmic X-ray background will be important in diluting the signal. Indeed, these clouds are also highly variable, both in flux and morphology. This is a comparison between 10 years of the molecular clouds in the galactic center, and as you can see, many of them have almost disappeared. So it was important to monitor which were the clouds that were the brightest at the time of the IXPE observation. This is a recent ART-XS observation of the galactic center from 2019, where we can see that Sagittarius B and C complexes have disappeared, but the Sagittarius C complex is still on. And indeed, it is the one that IXPE already observed for 1 megasecond a few months ago. In this field of view, as you can see from this iron K alpha Chandra image, many clouds can be observed at the same time, allowing us, in principle, to determine that if indeed Sagittarius A star was the source of illumination. Depending on the first year result, we will further observe this region for another megasecond in the second year. We did a lot of preparatory groundwork for this observation, publishing a couple of papers for which we discussed the feasibility study for each of the molecular cloud complexes and developed the data analysis techniques. Our aim, this is a simulation, don't sweat, is to determine, first of all, it's to obtain polarization maps like this, in which the X-ray polarization information can be related to the reflection emission in the galactic center. We want, first of all, determine if the emission is due to reflection by observing, by measuring polarization from the continuum emission. Then we hope to identify the scattering plane and thence the external illuminating source. And finally, if we are good or lucky, to determine the line of sight distance of these clouds. In conclusion, the take-home messages is that thanks to X-ray polarimetry, we can probe both strong magnetic field and gravitational field, investigate source geometries, magnetic field topology, and identify emission processes. IXPE is the first mission that is entirely dedicated to spatially resolved X-ray polarimetry, that it's flying and working, and it's allowing us to study faint extended sources, mapping their magnetic fields, and allowing us to distinguish the polarization properties in different regions. And through in-flight and ground calibration, we can validate the scientific result and check the good functioning of the detector during the initial lifetime. IXPE is working. A number of very secure detection, more than 10 sigma, have already been made public, such as Magnetar, Hercules 61, that is an accreting neutron star, and of course the Crab Pulsar Wing Nebula, but we already know that. This is already an out-of-date list because many other sources have been already claimed to be polarized, and the results are coming by the day. So after a 50 years hiatus for X-ray polarimetry, thanks to IXPE, this field is back. And the end game is to finally complete this picture and obtain at the X-ray energies the same level of polarimetric capability and detail that we have at other wavelengths. Thank you for the attention.
Thank you, Riccardo. That was wonderful. So, do we have any question from the audience?
Spatial resolution. Okay, for imaging, since we have three detectors with three different telescope modules, each one has a slightly different spatial resolution that goes from close to 20 arcseconds for the best to 30 arcseconds for the worst. Actually, there is a spare model that has an even better angular resolution, but it was not installed. It is a pity. As for polarization resolution, well, that depends on the statistic that you accumulate. So for a very bright source, you can go down to a less than 1% minimum detectable polarization in a short time.
Is there any hope of getting the polarization from the green light feature?
One of the requirements for the angular resolution was indeed to distinguish the pulsar of the crab from the torus. Yes, in principle, it is possible.
Thank you.
Okay. Also, this reflection of X-rays in the galactic center. Surely it's interesting to compare this to radio changes in the galactic center. Happen a good deal more slowly. Or anything that's happening fast has to be a reflection and not an actual change in the thermodynamic properties of molecular material around the galactic center. Right? So, you don't need a polarimeter to know that it's in fact a reflection. It might help where it's coming from, but it's probably coming from such a star.
The circumstantial evidence is very strong, but this would be the last nail in the coffin, because you have really like a compass telling you where the external illuminating source is.
More questions from the audience here? No?
One other quick question. Temperature effects.
So on the detector, yeah, on the detector, the thermal effects are under control. This has been studied during the calibration phase. But indeed, this boom motion is thermal induced to the night-day cycle. And in hindsight, I don't know why it was not expected, because I think it happened also in NuStar that has a very similar boom.
I might have a question. So you showed just a picture of supernova remnant 1006.
Yes.
So the question about that. So you plan to do extensive observations. There is a paper of 2013 showing a radio polarization there, which had consequences for the large-scale orientation of the magnetic field. How long do you think you need to observe this in 1006, and how do you think this can improve, the X-ray polarization can improve in nailing down the question of the orientation of the magnetic field?
So each of these three supernova remnants has its own personality, let's say. And one of the peculiarities of SN1006 is that it's very big. So the field of view of IXPE will encompass only the northeastern limb. So we will point that region for 1 megasecond. Now, SN1006, among these three sources, it is the faintest. So in principle, it will be the one most difficult to observe, from which to detect polarization. But on the other hand, its spectrum is almost entirely non-thermal. So it will be less diluted by thermal emission that is present in TICO and CASE. So this could help us to offset the problem of its faintness to detect the polarization.
And when is going to be observed?
So until yesterday, the plan was to observe SN1006 in late July, early August, if I'm not mistaken, but we just received the news that there will be an update of the observing plan. So I don't know how it will shift around. While TICO will be observed starting from what day it is today, in 2 weeks.
Oh, okay. Oh.
Starting, and it will also be observed for 1 megasecond.
Oh. Thank you. Any question from the Zoom people?
So there is.
Oh, sorry.
I just wanted to see a source off axis. You know, when you're on axis, but nice symmetry in the optics, go off axis, break that symmetry.
So you do not induce polarization from the optics, thankfully. We checked it in the Straylight facility of the Marshall Space Flight Center during the calibrations, because you have still a symmetry of the mirrors, so any spurious modulations cancels out, and any residual induced polarization from the optics, I think it can be calculated from the Fresnel law to be of the order of 1,000%, while our resolution is of 1%, so it's not a problem. But indeed, one of the issues that rose during the observation is that we found that there was a small offset of the telescopes with respect to the detectors. And this was causing actually a slight reduction of the effective area. But this was corrected a couple of weeks ago.
Okay, so is there any question from the online people? I don't see. Yeah, sure, please.
So there's 31 periods of a million seconds in a year. You actually get something like 30 pointing per year out of this.
So
what's the overhead?
Let's see, I think I had some numbers, you know, it were before. We expect to observe for about 15 megaseconds in the first year, with sometimes also dedicated to a target of opportunity observations. The numbers close to the classes of sources is the number of the sources of each class that are in the first year plan. The first year observation plan is fixed apart for the targets of opportunity, and I think the second year plan is being drafted. And then there will be, given that there are no consumables on board and that it's in a high orbit, IXPE can endure for a long time. There will be also a guest observing program after these first 2 years of operations.
Right. Oh, just what Riccardo, can you go back to the picture with this?
This one?
Just a comment about these. Maybe passengers might emphasize, because it's been asked what the angular resolution of the telescope is, which is not great. But the beauty of the supernova remnant observations is that we look at the rims of these things. May get a blurry image, but the static images show us those thin blue rims where the coming from. So we actually know when we're probing really close to the shot, closer in fact than radio observations. We know really very close.
Thank you. Okay, so there are no more questions. Let's thank our speaker again. And we'll see you maybe.